Okay, folks, so we're going to look at Chapter 13, Problems 5, 7, and 8. This is our aqueous metal chapter. So, once again, not going too far in depth, not asking you too much math, but more theory questions. Question 5 involves us to examine a table which reports data relative to the stability of complexes between various metals and NTA. Comment on the relative values of the table in terms of the environmental classification metals. Predict the approximate pKa of nickel 2, mercury 2 based on the following classifications. So, real quick, let me pull up the table if I can. Let's zoom that in. Oop, too much. There we go. Hopefully this will be. So we're looking at a table that looks something like this. So we want to see where nickel 2, mercury 2 it should be based on those numbers. Nickel 2 plus and mercury 2 plus. Mercury 2 plus is right below zinc. So it's larger than zinc, but it's the same classification as zinc. Nickel 2 plus is adjacent to copper and cobalt, so it's probably going to be in the borderline area. And with zinc and mercury 2 plus being in the type B. However, so in general, type A is less than the borderline, which is less than type B, but there's also, we see factors increases with charge. And we see, if we can look in this table, you can see nickel 2 plus right there, firmly locked in with cobalt, and actually zinc. While mercury 2 plus is way over here, up above in the type B, way different from zinc. So if anything, mercury is a nickel 2 plus, going to be somewhere between manganese and copper, and mercury is going to be somewhere between zinc and lead. So right between 10.66 and 11. That, in fact, we see that, though I think they have put in this in terms of stability, that copper 2 plus is going to be less than or equal to nickel, which is less than or equal to zinc. And so I had, I think zinc is, it's going to be somewhere between copper and zinc and whatnot. So it's actually probably close to 12-ish. 12-ish maybe. 10-ish, 12-ish. Wow, like mercury 2 plus is going to be comparable to, you could say, maybe between copper 2 plus and iron 3 plus. It's a higher charge, but also bigger. Way up here in the type B. And so it's going to be closer to like maybe 12-ish, 13-ish. So it's kind of a little rough idea. But we have increasing stability as the downward diagonal, so mercury is going to be a little bit less acidic than, say, nickel. So that one's kind of a rough one. Let's look at So basically nickels, like I think according to the book, well, they said approximately 12, and mercury is approximately 13.5, but I'd say it's very similar to lead. You would say that it's very similar to lead, and mercury's gonna and nickel's gonna be similar to cobalt and maybe copper 2+. So it's a little weird one. 7 is a little bit easier. Note the electronic structure of cadmium-2 and indicate whether you would expect this to be type A, borderline, or type B, which should be placed. Predict the principal inorganic forms in the elemental and fresh or salt water for both oxidizing and reducing conditions. So to do this, look at what is the electronic configuration of cadmium, and then make it cadmium-2+. So cadmium is right there up below zinc. So it'd be cadmium would normally be something like this. That's cadmium neutral. Cadmium-2+, X's out that. So this cadmium would typically be a type B or / borderline, a little bit between the two. So we would want to look at species similar to what zinc can do. Species to what zinc can do. So that means you might expect some cadmium chlorides of various types, like cadmium chloride 1, cadmium chloride 2, cadmium chloride 3. It typically remains cadmium-2+, but under strong reducing conditions, it can go to cadmium solid and cadmium-2+ in oxidizing conditions. And we might expect to see some cadmium. We might expect to see some cadmium solid, cadmium sulfide. And you might expect some cadmium hydroxides in basic conditions. So basically I'm just taking some of the looking at what zinc can do and comparing them to them. And finally, 8. This is the one where it actually makes you think a little bit. Artificial zinc, for example, in low pH, it remains zinc 2+. In moderate pH, it can be zinc hydroxide, zinc chloride. In moderate pH with reducing environments, the same. Under very basic pHs, it's zinc dihydroxide. Under both. So I'm basically kind of copying some of the same. Now the last one's one where actually kind of, instead of reading tables, to make some thoughts. The last one says, okay, artificial natural wetlands are frequently used as catchment basins for urban runoff and stormwater. The sediments in these basins have some ability to extract and retain soluble metals from the water as it flows through the pond. For lead, cadmium, and zinc, use information in this chapter elsewhere to predict the affinity of each of these metals for the carbonates, iron oxides, and organic matter fractions of sedimentary material suspended or settled in the pond. So expect whether you would see these binding to hydrous iron oxides, form in the form of carbonates, or into organic matter with acid. So looking at lead 2+, then we want to look at zinc 2+ and cadmium 2+. All these are kind of borderline, a borderline or type B. So all these have some affinity to all of these guys. That cadmium carbonate, cadmium lead carbonate, and zinc carbonate both have a pretty high pretty low KSP. That I can look that up and say, in this case, so for example, cadmium carbonate has a KSP of 5.2 times 10 to the negative 12. Zinc carbonate has a KSP of 2.0 times 10 to the negative 10th. And lead carbonate has a 1.5 times 10 to the negative 15th. So, meaning they are not very soluble in carbonates. That as we go down the table, zinc, cadmium, and lead, we see the solubility decreases. So, heavier means they're less soluble in this case. More type B covalent character. As far as the bonding with humic material, both we can find data for both lead and zinc that are pretty good. So we could probably predict cadmium being similar. With I can looked up, and lead is like what 1.1 times 10 to the 4th for the KF of bonding to humic matter, and zinc being what like 4.0 times 10 to the 3rd for the KF. So yeah, I'd say cadmium is probably going to bind with humic matter. As for iron oxides, yes. Iron oxides, the sedimentary material of iron oxides can remove these various species. So yes, it all depends on how soluble they are. For example, humic matter, if it's part of the soluble components, will grab and transport these guys into downstream. However, if it's part of, say, the insoluble particulates, it's going to catch and allow these to settle to the bottom. Or if it's coating these iron oxides, it's going to catch and settle to the bottom. If these are neutral conditions, the iron hydroxides or iron oxides are going to be insoluble and capture some of these components. Especially that will favor carbonate formation. But under acidic conditions, both the carbonates will decompose as well as the iron oxides will dissolve and release these guys back into solution. So that's just some thoughts of this. So I didn't do a lot of math of this chapter. I just kind of some conceptual comparing problems. So that's a little quick rundown of this chapter. See you next time.